Hello everyone, I'm Paul and today we're solving problem 3403. Find the lexicographically largest string from the box 1. For this one, the intuition is key. So here I will show you what's my thought process and how to solve this. We are playing a game here. We are given a word and an integer which represents some number of friends, and this game has rounds. In each round, the word is split into number of friends non-empty strings such that each split is unique, and we put all the unique split words into a box, and after the final round we return the lexicographically largest string. So let's say we have this word and we have two friends. In the first round we can give a D to one friend and B, C, A to the other friend. In the second round we can give D and B to one friend and C, A to the other friend. And in the final round we can give D, B, C to one friend and A to the other friend. So here we have 6 unique splits. And from this we need to return the lexicographically largest string, which in this case is DBC. Now, in case you don't know what lexicographically largest means, let's say we have a string, DBC for example, and we are comparing this with, let's say, FG. Well, in this case, we are checking characters from left to right, and as soon as we find different characters, we check which one is greater, and that's the lexicographically largest string. So for example, we are comparing D and F first, and F is greater than D, so FG is lexicographically larger than DBC. Now let's say we are comparing DBC with DB, and we are following the same process. So first D and D are equal, then B and B are equal, and then we have no character here. This means that we are keeping the longest string. So in this case, DBC is lexicographically larger than DB. Okay? Now going back to a problem, let's say we have this, we have DBCX as the word, and we have two friends. Now the question is, how can we get all the unique splits in a reasonable time complexity? Well, first we can check what's the largest split that we can make. Let's see how this works. We have two friends, and as a minimum we need to give one character to each friend. So we give one character to the first friend, and we can give all the remaining characters to the other friend. This means that our biggest split has a size of 3. And we can use a formula for this. This is n minus number of friends, we can call this f, plus 1. So in this case, 4 minus 2 plus 1 is 3. And remember, this is the largest split we can make. And we will call this target. So this is 3. And with this in mind, we can iterate the word from left to right in steps of target, and each time we will get unique splits, and more specifically we will get the maximum unique splits. So we start here and we take DBC, we'll put DBC here just to know that we have this, and remember, this is the maximum split that we can make. But we also need to make smaller splits. We need to make splits of 2, we need to make splits of 1, but here in DBC, if we take a split of 2, for example, we know this will be smaller than DBC because of how we are comparing strings. That's what we saw a few minutes ago. If we compare DBC with DB, DBC is greater, and if we compare DBC with only D, DBC is still greater. So it doesn't make sense to use these splits here. We'll only use the biggest split that we can make. So now we continue and we get BCX. So we put BCX here, and we know that DBC is still the lexicographically largest split. And next we end the loop, and this is almost it, but we are missing a very important part. Remember that we didn't care about this split of 2 and the split of 1 because we were iterating this from left to right, and this means that the split of 3 will always be lexicographically larger than this and this. But in this case it's different. We want to consider 2 and 1 for the splits from the end, because let's see what happens. We already have the split of 3 from the end, so we have BCX here. Let's say we take this split of 2. So we are taking CX and we put CX here. DBC is still lexicographically larger than CX, but we also need to add the split of 1. So we add X to our unique splits, and now X is lexicographically larger than DBC because X is larger than D. So the final answer for this one is X, and this means that only for the end part we are considering anything below our target. Okay, so this is it for the intuition. I know this can be tricky, but if you didn't get the idea, you can see this video one more time. And now let's go with the code, and hopefully you will get the idea. First, if the number of friends equals 1, we return the word as it is. And now n equals length of word. Target equals n minus the number of friends plus 1. The selected word is initially an empty string, and now for I in range from target minus 1 up to n, current will be word, and here we'll take a substring. We'll go from I minus target minus 1 up to I plus 1. Remember, the left part is inclusive and the right part is non-inclusive. And now if not selected or current is greater than selected, selected equals current, and now for the final part we'll say current is an empty string, and for I in range from n minus 1 up to n minus target in steps of minus 1, this means in reverse, current equals word at I plus current. This means we are adding characters to the left of current. We are doing this like this to preserve the original order of the substring. And now if not selected or current is greater than selected, selected equals current, and finally we return selected. So this is it for the code, and now let's submit this and see if it works. As you can see, this works and it's very efficient. Time complexity for this will be roughly big O of n squared, because we are iterating and slicing the word, and space complexity will be roughly big O of 1. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.